Okay, in this video, I'm going to introduce, or I guess reintroduce, since I've already talked about this in class, the concept of a Cauchy sequence. Now, up until this point in class, not so much now because we've talked about things, but up until the point when we talked about Cauchy sequences in class, if we wanted to prove whether or not a sequence converged, or if we wanted to talk about a sequence converging, from the definition, we have to know what L is. If we want to use the definition of a limit, we have to know what L is, and we have to show that for all epsilon, there exists an in such that such and such a thing is true. But that such and such a thing involves the limit L directly. And so basically, if we want to show that a sequence converges, we have to know what L is, or we have to know some other property. Like the squeeze theorem. We have to know AK less than or equal to BK less than or equal to CK. We have to know the AK and CK are both converging to something. But in reality, we don't always know what that limit is, or we don't always have a guess of what that limit should be. But we do know that maybe the terms, as you go far enough along the tail end of the sequence, if you look at the tail end of the sequence, all of the terms are getting closer and closer together. You might not know what they're getting closer together to, but you know they're all getting closer and closer together. So for example, after a certain point, you know all of the terms are going to be within epsilon of each other. And then maybe you go a little bit further and they're all within one half epsilon of each other, and so on and so forth. So you know that the tail end of the sequence, as they're kind of getting smaller and smaller and smaller, or not smaller and smaller and smaller, but they're getting closer and closer to each other. And so we would like to be able to conclude from that the sequence converges, and it is a reflection or a result of the completeness property of the real numbers that's true. And actually, when we talk a little bit about metric spaces, which we won't talk a lot about, but when we talk about the metric space properties of R, we'll actually see that when we talk about completeness, in a metric space, this really is the definition of completeness. Okay, but for real numbers, things are a little bit different because they have more structure. Okay, so let me just define what a Cauchy sequence is. And it wants to, the definition of Cauchy sequence is supposed to capture this idea that if I go far enough along the sequence, that eventually the tail end of the sequence, all of the terms are close to each other. So if AK is a sequence, I've restarted my computer and closed stuff, so hopefully the videos are, hopefully writing on the screen will go a little better. So if AK is Cauchy, nope, I guess not. If AK is Cauchy, sorry, you know, this is distracting me so much. If AK is a sequence, we say it is Cauchy if for all epsilon greater than 0, there exists an in such that for all k and L bigger than n, AK minus AL is less than epsilon. Okay, so remember, what idea is Cauchy sequence supposed to capture? It's supposed to capture the idea that if I go far enough along, that the tail end of the sequence, if I look at the tail for, if I go far along enough in the sequence, all the terms in the tail end of the sequence are going to be close to each other. And that's what this says. For all k and L greater than n, that is for far enough along, AK minus AL is going to be less than epsilon. In other words, small. So for all epsilon, I can go far enough along in the sequence such that after that point, all of the terms are going to be within epsilon of each other. Okay, in the upcoming videos, I'm going to give some properties of Cauchy sequences, and this will culminate in the important property that if we have a sequence of real numbers, then it converges if and only, then the sequence converges if and only if it's Cauchy. Okay, the hard part of that proof is to prove that if a sequence is Cauchy, then it converges.